get into negative work. Okay? So what you'll see is a lot of things we've already talked about kind of come back into focus. What's the only reason that I had to apply that 0.8 newtons of force to keep it moving? Deacon.
Friction.
This is friction. If there was no friction, if this was the magic frictionless block, and I gave it a push, what would it do?
Keep on sliding.
Just keep going. Inertia would keep it moving. Okay? So I would do work to push it, but once it was moving, I wouldn't have to do any work because of the fact that there would be no force necessary to keep it moving. So here's where you can get into negative work. So negative work is going to happen in two situations, where it's in the opposite direction of motion or you're lowering something down. So here's the story. So when's next week supposed to finally get cold, low, down to maybe like 28? So you walk outside and you've lost your mittens and your hands are cold and you're gonna do this, right? Try and warm your hands up. Are you doing work when you do this?
Yes.
Yeah.
Thatcher. If I do this to warm up my hands, am I doing work?
Yeah.
Why?
Your hands are moving.
And I'm exerting force over a distance, right? Okay? Now, when you do that, that generates some amount of thermal energy. That's why your hand feels warm. So basically, you're forcing the electron clouds of one hand to move past the electron clouds of the other. They don't like that. They get upset. They go, oh, this is bad, okay? And they throw a little tantrum, and you feel that as heat, okay? But let's say that you don't understand physics, and you go outside, you go, oh, man, my hands are cold. And you do this, okay? You don't understand physics. Why is that not going to warm up your hands? What's missing? Friction, right? Now,
Point proven.
so if when this thing gets pulled, there's going to be work done in overcoming friction. So the frictional force is in the opposite direction of motion. So the work done in overcoming friction is going to be negative 0.80 newtons times 1 meter, which is going to get me negative 0.80 joule. Okay? So that's work done in overcoming friction. So when I pull this block, just like when you push your hands together, there's a certain amount of thermal energy that's generated. When I pull this block, there's a certain amount of thermal energy created by the friction between the block and the book. Okay? Now, if you've ever seen any of like the survival shows, Bear Grylls, okay, and they're out in the middle of nowhere and they need to start a fire, what do? Rub 2 sticks together, right? So they take a little piece of wood and they hollow out a depression, and then they took another stick and they kind of do this, right? And they push down and they rub like that. Are they doing work? Yes. And that work is generating heat. And if you generate enough heat, you get a little bit of spark and you have made fire. Okay? But if you're out there and you go, man, I don't want to do any work. I don't want to sort of force through a distance. Guess what? What are you not going to start? The fire. Because you're not going to do any work. Okay? Now, obviously, I don't have to, if I pull this across here, I don't have to worry about the book catching fire. It's like, what happened to the physics book? I pulled a block across the surface of the book. Okay? Obviously, I don't have to worry about that. Is there a little bit of thermal energy? Yeah. So this is like a bookkeeping thing. So I do positive work to pull it. I do an equal and opposite amount of work in overcoming friction, which is generated as thermal energy. Okay. So, let's say I take a rubber stopper and I swing it around my head like this. Once I get it up to speed, Luke, am I doing work? Once I get it up to speed?
No,
Why not?
because you're not applying any force.
Really?
Wait.
Oh no!
I wasn't applying a force. Stopper me. Oh, God.
Oh,
Just throw the stopper. Just throw the stopper.
throw the stopper, the string will fall.
Okay. All right. So, if this thing is moving around in a circle, you're telling me I'm not exerting the force?
Can they help?
Yes.
So I'm gonna say that we are doing work because, oh look, you're going in a circle.
Okay,
So
look,
has to
if
be-
this goes around, what's the... Save me, please.
Okay. Yeah, you are doing work because you're exerting a force on it and it's going in the direction you're exerting that force.
Hold on. Okay, here's the rubber stopper. What's the direction of the centripetal force?
Inward.
Inward, at a right angle to the velocity vector. So is there a force being exerted?
Yes.
Yeah.
Yes. Is that any different than me just holding up the stopper like this? Am I exerting a force?
Yes.
Is there a displacement in the direction of the force?
No.
No. So once I get this thing up to speed, now I do work to get it moving, okay? But once I get it up to speed, what's the direction of the force?
Inward.
Is there any displacement in the direction of that force?
No.
Guess what?
There's no force.
There's no work being done. Now, if I do this, then would work be done?
Yes.
Because then there would be displacement in the direction of the force. But if the radius stays constant like this, okay, the force is acting inward, but there's no movement in that direction. That's like me holding up this block. I'm exerting a force, but it's not going anywhere. But if I lift it up, then do I do work? Yeah. Okay. Now, vertical motion gets a little bit tricky. So let's say Scooter is going to move off to college. And Scooter's going to have, to make the math easy, a small little refrigerator that has a mass of 10 kilograms, which is about 22 pounds. Okay? And the bed of the truck is 1 meter above the ground. Okay? So we got to get this 10 kilogram refrigerator into the bed of the truck. Is work going to be done? Sydney?
Yes,
Yes. Why?
you're gonna apply a force over displacement and the object's gonna move in the direction of the force.
How much work am I going to do?
Lots.
Lots.
10 joules.
10 joules. Everybody cool with 10 joules? None of you should be cool with 10 joules. What units does joules have to be measured in?
Kilogram meters squared over.
Or Newton meters, right? Newton meters,
Said it wrong.
right? If I multiply kilograms times meters, do I get Newton meters?
No.
No. Do I get joules? No.
At least 10 joules.
Now, what does a 10 kilogram refrigerator weigh, Andrew?
98 newtons.
Now, if I take 98 newtons and apply that to lift it up to a height of 1 meter, then
You could gonna be
I do work measured in,
joules.
which would be 98. So if you're a graph kind of person, like, oh, Mr. Burkamp, I was president of the Physics Graph Club. Cool. So here's the idea. You exerted a force of 98 newtons over a distance of 1 meter. And so that was 98 joules. Now, in addition to the refrigerator that Scooter got, Scooter, which is kind of cool, also got the magic frictionless ramp. That's 2 meters long. So that's 1 meter, this is 2 meters, that makes that a 30-degree angle. Now, obviously, she can't walk up the ramp and push it because it's frictionless, okay? Bad things are going to happen. So Scooter, being smarter than the average scooter, stands up here and goes, I'm going to take a rope and I'm going to pull it up the frictionless ramp. Will she do more work or less work or the same work using the frictionless ramp? Connor S.
What? Same.
Why?
Because
He was clearly not paying attention.
Andrew?
Because you're moving it over the same vertical distance.
I was paying attention. Thank
Or-
you.
I'm thinking weird
I didn't
again.
give any answer.
I wasn't paying
sorry.
attention. Pick somebody else.
Deacon?
I would say the same, it's gonna be the same positive work, and there's gonna be no negative work.
Okay. How do you, but fundamentally, what do you multiply together to get the work?
Force and distance.
Okay? So what force does the scooter have to overcome to pull it up the ramp?
Force parallel.
Force parallel, right? A component of gravity, force parallel. Connor A, how do you calculate force parallel?
So does
Force gravity, cosine,
Nope,
sine.
sine theta. So if I take 98 newtons times the sine of 30 degrees, trust me on this one, the sine of 30 is 0.5, you get 49 newtons. So, will Scooter have to apply less force to pull the refrigerator up the inclined plane? Yes.
Yes.
She only has to exert 49 newtons of force, as opposed to the 98 just to lift it. But, what's the trade-off?
It's a greater distance,
There's a greater distance.
so it's the same.
There's a greater distance.
Same area.
So now, to get the work done and using the magic frictionless ramp, I'm going to take 49 newtons times 2 meters, which is oddly enough, it's going to get me the same 98 joules.
So that's why we-
Okay? So if you go back to the graph, if you go back to that, so now we're going to exert a force of 49 newtons, but we're going to do that over 2 meters. What do you know about the two areas? They're the same. Okay? Now, the one thing we haven't talked about is time, okay, in terms of work. So, one of the most important equations is this, is that power, upper level, uppercase P, and there's a couple different ways that you can view this equation. One is that it's work done divided by time, okay? So, work is going to be in joules, time is going to be in, so it's joules per second. Otherwise known as watts. So, where have you all seen watts before? Watts, microwave, right? 1,000 watts. Typical microwave is 1,000 watts, which means that that's emanating 1,000 joules of energy per second. Okay? Where else have you seen it?
In the electronics.
Light bulbs, right? Light bulbs. Typical household light bulb might be 100 watts, might be 80 watts, might be 120. The higher the wattage, what do you know about the brightness of the bulb? It gets brighter because there's more energy per second. Okay? So, watts, joules per second, work per unit of time. The other way that you can view this is that it's change in energy per unit of time. Okay? So when you look at this, and this is the broader idea, and we're going to use this again and again and again and again and again and again and again. So we're going to get into energy. We're going to spend a lot of time talking about energy. You might have rotational kinetic energy. You might have linear kinetic energy. You might have thermal energy. You might have electrical energy. So any change in energy, no matter what it is per unit of time, is going to be in watts. So if you look at like an insulated thermos, what's the idea of an insulated thermos in terms of change of energy per unit of time?
Increase the change of energy.
Yeah. Like, let's say you put some hot soup in there. What do you want the soup to do?
Stay hot.
Stay hot. You want a very low rate of thermal energy flow per unit of time. Okay? So there are times you want a very, very, very small value of energy flow per unit of time. Now, you get home and it was like, hey man, I want to make popcorn. You're going to throw it in the microwave. If that's the case, what do you want in terms of energy? You want a lot of energy per unit of time. It's like, oh, I'll throw some microwave popcorn in. How long is it going to take? Oh, 4 hours. Okay, well, that's going to take a while. It's like, well, we'll get it popped, but it's going to take us 4 hours because of the fact that we don't get very much energy per unit of time. Okay? Yeah, but you don't want an extreme case. You don't want like 10,000 watts. It's like, how long does it take you to pop microwave? Oh, about 2 seconds. Bam! Okay?
10 kilowatt
Well, yeah, so-
microwave.
Well, yeah, that would be like the death of a microwave. Now, here's the other way that you can view this. Power is work divided by time. Luke Etheridge, what's the simplest way to calculate work? No, calculate. Those are the units. What can I multiply together to get work? If one rhymes with Orse.
Distance.
Force and distance. Connor M. If I take distance and divide it by time, what do I get?
Velocity.
So I can also write this as force times velocity. Okay? Now, if you ever own a battery-powered car, you need to be keenly aware of this equation. Because your batteries only contain a finite amount of power. Okay, that's it. It's a finite amount. So here's your car. Let's say you're driving down to Dallas. And you're fighting a strong south wind. What's going to happen to the force side of that equation? It's going to get bigger, right? Because you're driving into the wind,
Yes.
right? So what's going to happen to your power consumption? It's going to increase. So your battery is going to run out faster if you're driving into the wind. But then, even worse, you decide to drive fast. So if you're driving into a strong south wind at 80 miles an hour, what's going to happen to your power consumption? It's going to go way up. Now, if you're driving with the wind, though, however, if you're reversed it and you're driving with the wind, then what's going to happen to your power consumption? It's going to become less. Okay? So if you ever drive a battery-powered car, you need to be aware that your power consumption is force times velocity. And the faster you go, what do you think happens to the frictional forces with the air?
Increases.
It increases. So the faster you go, it does become an exponential decrease in your power. Because the faster you go, the more wind resistance there is, the more force that you have to put into it. There you go. Okay, stop you on the camera.